So now we will continue and try to analyze the competitive ratio of the randomized marking algorithm for the paging problem. So randomized marking. Now, just to refresh our knowledge on this subject, so that was the paging problem. So for example, of course the cache size in our examples is always 3, but it's not a realistic cache size, never mind. And we will just get some sort of input like say 1, 3, 2, why not 2 again, and then 5, why not 3, 5, 2, 1, let's say 4, 1, 2, 5, and say 3, like this. Then remember, a marking algorithm is just doing the same thing over and over again. So I'm just starting with an empty cache, and then I'm moving to the state when I have something in the cache, but when I access an element in the cache, I mark it. And marking is always just some sort of protection from being discarded, at least for a while. And then I'm just putting the 2 into the cache as well and mark it. And then for this particular input, I don't have to process for cost because it's, well, already in the cache. And then for processing the 5, I have to discard something from the cache. So this was an end of a phase, and this was the beginning of the very first phase. This was the end of this phase. Just remember, we were dealing with phases. And at this point, I have to discard somebody from the cache after removing all the marks. So yeah, thickness is okay, thanks, great. For this case, I will have 1, 2, 3, and then I have to discard one of them. And we've seen that it doesn't matter which one we discard. So for example, we can discard the lowest one, the highest one, or just the one having the least recent timestamp. That was the least recently used algorithm, and it will be k competitive. But if we use a random, it can be better than that. So for example, here a randomized marking algorithm can discard either this or that page from the cache, and a randomized means that we will discard the one which we choose uniformly at random. So this means that with 1/3 probability, I'm discarding the 1, and I will have so the 2 and the 3 and the 5 marked. But with probability 1, I will have 1/3. I will discard the 2, so in this case I will have the 1, the 3 and the 5 marked. And then with probability 1/3, I will discard the 3, and I will have the 1, the 2 and the 3 and the 5 marked. So that 3 possible configurations I will be after processing these input of 5. And here, for example, if I choose the first path, then the 3 is free because it's in the cache. So in that case, I won't have to discard anybody from the cache, and I will have the 3 star, because it's got accessed 5 star. And then in this case, it's still free, and then I still have to mark the 3. But in this case, I'll have to discard either the 1 or the 2, because I have to discard an unmarked page. So with 1/2 probability, I will discard the 1 and load the 3. Now this will have a cost. And with 1/2 probability, I will just discard the 2, and I will have the 1, the 3 star, and the 5 star, right? So right now there are 4 possible computation paths, and the first one was just with probability 1/3, the second one was probability 1/3, and the next 2 are with probability 1/6, because there is a probability of 1/3 and the probability of 1/2, and these have to be multiplied, of course, because it's a conjunction of these independent things. Now, if I'm just processing the 5, it's free for each possible running stuff, so I'm just skipping this. No, I'm just writing this down, so it's again 2, 3 marked and 5 marked, and then I'll have 1, 3 marked and 5 marked. Now the interesting thing is that no matter which path you use, the number of marked pages is always the same. Actually, that's why the algorithm is defined this way, because it makes it a bit easier to analyze. So if we just now process the 2, then this guy here doesn't cost us anything on this path, but we have to mark that, and we already have the 3 marks. Here I have to discard the 1, but now I don't have any choice. This is the only page which can be discarded, so here I'm discarding the 1, and I will have the 2 and 3 and the 5 in the cache. Here 2 is great because it's in the cache, so it's fine, it's free, but here I also have to discard the 1 and load the 2 and mark it immediately. And then, no matter in which configuration I am, the 1 will start a new phase because it's not contained in any of the possible configurations, and everybody and all the elements of the cache are marked. So I'm just marking the end of the phase. I won't do the simulation for the war stuff. I just want to recall that a phase is the longest possible run containing exactly k different elements, or for the last one it can be less than k, so it's the longest possible run containing at most k elements. So it's again 3 elements, the 2, the 3 and the 5, and here it will 1, 4 and 2, so that will be the third phase, and here it's just a bit smaller than k, but that's the last phase, so it's not finished. Now a marking algorithm after a phase, the cache configuration will be always the set of elements of the phase. So for a marking algorithm, no matter it's randomized or not, the cache configuration is definitely 2, 3 and 5 at this point. You can verify that this is the same as we've got in this last column, so it's fine. After the first phase, it's always 1, 2 and 3. Now this holds only for marking algorithms. So in general, if you run an arbitrary algorithm, possibly the optimal one, you are not really required to do this. So it's a bit harder to compute the optimum, but if you use the marking algorithm, then that's for sure you will contain all these elements. Now, so that's the randomized marking algorithm, and for this particular example, let's try to compute the cost, the expected cost. Remember, we have to compute the expected cost. I will try to so mark those transitions which have a cost. So for example, here we have a transition having a cost, and then each of these transitions have a cost as well. Now here, this guy here doesn't have any cost because 3 is already in the cache, and here 3 is already in the cache, but here this guy and this guy have cost because they have to discard something and load the 3. And then none of these guys will have a cost because 5 is contained in the cache. So it's it's a good thing to realize that within a phase only the first occurrence that matters. All the other occurrences are free for a marking algorithm because it's already in the cache. So you just load it in the beginning of the phase into the cache and mark it. So during the phase you won't unmark it because unmarking happens on the bounds of the phases. So you will have still, in this case, the 5 contained in the cache marked, so you won't have to pay for the second occurrence. So we only have to deal, when we just compute the cost for a marking algorithm, the first occurrences of each request in each phase. So it's always free. And then here it's free because the 2 is in the cache. Now this guy has some cost, this is free, and this guy also has some cost. So we have 4 possible computation paths till this point, but I'm not running the simulation. So in this case, so it's 1, 2, 3, 4, okay, and the first run is it possible that it doesn't spend anymore? Yeah, okay, so it's 1, 2, 3, the cost is 4 in this case. Now in the second case, I'm just zooming out a bit. Now in the second case it's 1, 2, 3, 4, 5, it was 5, right? Okay, 5, it was 6, this was also 6, and this was 7, I presume. And I have to use the probabilities here, so I will have the 1/3 here, and the 1/3 there, and the 1/6 here, because there was a probability of 1/2 and another probability of 1/3 in the beginning, and then there's the 1/6, and then I have to sum these, and that will be the expected cost. So that's well, it's 7 over 6, it's 6 over 6, it's well 6 over 3, which is 12 over 6, and this is just 10 over 6. So it's, if it's something over 6, then it's 12, okay, 22, so it's 37 over 6. Now that's slightly larger than 6, which means that I made an error here, because this sum is so it's 13, so it's 35. Okay. So it's just 35/6. Yeah, right. It doesn't really matter the exact value, but it's of course smaller than 6. That was my sanity check. That was my sanity check because these guys were in the middle and that guy had a slower probability than that guy, so it should be smaller than 6. Anyways, so the expected cost of the randomized marking algorithm on this particular input, yeah, so only on this one, is just 35/6. And of course the optimum is probably 5 because we have 5 different elements and we already have a run of this algorithm of 6. So the algorithm divided by the optimum cost for this particular input, the expected cost of the algorithm divided by the optimum is 35/6 divided by 5, which is 7/6 in this case. Now this is the ratio which we want to compute in the general case for arbitrarily long sequences. And for that, we will first analyze the optimum. So we will analyze the optimum for a fixed sigma. We first analyze the optimum and get some bound of the optimum of sigma being at least as large as sum O. O is not a good choice because it can be confused by a 0, so it's just L, like lower bound. It will be larger than some value L. And then we will analyze, and this is the harder part, the expected cost of the algorithm, and it will be at most some U for upper bound, and for these two we will get that the algorithm, the expected cost of the algorithm, which is the default for randomized algorithms, divided by the optimum value is at most U divided by L, because I'm increasing the numerator, right, and decreasing the denominator, so the value of the fraction will be upper bounded by this guy. Yeah, so I just have to tell an upper bound for the optimum and tell a lower bound for the optimum and an upper bound for the expected cost of an algorithm. This is always the case if we want to bound the competitive ratio. Now, okay, so let's move back and I will just try to introduce a bunch of definitions. So I will be an index of a phase. It will index phases. So this is the first phase, this is the second, this is the fourth, and this is the third, and this is the fourth phase. Now, in each phase there are new elements and old elements. So okay, so let Ti be the number of, say, new elements so this means that requests in phase I which didn't happen. In phase I-1. Okay, we will heavily use these TIs in our formulas to bound the optimum and the solution of the algorithm. So for this particular input, for example, here T1 is the number of new elements in the first phase, is 3 because, well, all of the elements are new. Now in the second phase, 2 and 3 are not new elements because they occurred in the previous phase, but 5 is a new element, but it's only counted once. Of course, each element is counted once, so this Ti is always a value between 1 and k. Of course, the very first request of a phase is always a new element, so Ti is always at least 1. So T3, so for example this one here is a new element because it didn't occur in the previous phase. It was occurring, of course, during the first phase, but it doesn't matter at this point because in the marking algorithm it's pretty sure that at this point we only contain these guys in our cache, so it doesn't matter whether an element occurred sometime previously the previous phase. So T3, 2 is not a new element, but 1 and 4 are, so it's 2. And then T4, for this particular example, T4 is so 5 is a new element, 3 is a new element as well, so it will be 2. Okay? Okay. So let's try to bound the optimum first because it's easier. Let's try to bound the optimum first because it's easier. So first, I'm just checking back to and somewhat less devilish color. So first we bound the optimum value using these TIs. Recall that we need that something optimum is at least as such as blah 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 here. Now, so okay, so we have an input sigma, and there are these phases. Okay, I'm just drawing these phases again. The last phase isn't necessarily complete. Now here, it's pretty sure there are, well, T1 different, so k equals T1, that's for sure in the first phase. If there are no k elements at all, then all the algorithms are optimal because everything is just loaded into cache, and that's also it doesn't really pay off to consider those inputs having only one phase because everything is optimal for them. And then during the second phase there are T2 new elements which haven't occurred here, which means that for this 2-phase long part there are, say, T1 plus T2 different elements. So in this case there are k plus T2 different elements because these elements T2 are exactly called new because they are not contained here. So there are k plus T2 different elements. Now this means that since here I'm starting with the empty set as in the cache, and this part will occur me at least k plus T2 k plus t2 cache misses. Now let's just try to consider this part here. The number of different elements during these two phases is k plus t3, right? K plus t3, because here t3 new elements occur. So here the number of different elements is k plus t3. Now, no matter what my cache content was, my cache at this point only contains k elements. Which means that I have k elements and I got a request for k plus t3 elements, which means that there are at least t3 cache misses during this period. Okay, and then let's consider these two phases. Again, we have k plus t4 elements, which means that no matter what was my cache content here at this point, during these two phases I will have at least t4 cache misses. And for the last part, for the last two phases, I will have at least okay, so let's call it say L for last. Last phase. So the last two will also induce at least TL cache misses. No matter which algorithm we use, the optimum will cost at least TL on these two phases in total. What does that mean? It means that if I'm just sum the number of cache misses, then for this part I will get at least TL. And if I'm just add this part here, it's at least TL minus 1. Blah blah blah. For this part it's at least T3, and for this part it's at least T2, and of course for this part only it's at least T1. It's equal to T1. So if I just sum all of these red things, then I include the error for a segment twice, right? So if I'm just sum these TIs, and divide it by 2, and here the sum goes from I equals 1 to L, and divide it by 2, it's at least so it's a lower bound for the cost of any algorithm, so it's a lower bound for the optimum value, right? Once again, so if I'm just add all the numbers, then I'm just adding something which is smaller than the total number of cache missing during this interval, plus the total number of cache misses during that interval, plus the total number of cache missing during that interval, plus the total number of cache misses during this interval, and each cache miss is right now computed or added to the sum at most twice, because cache misses occurring here are added twice, cache misses occurring there are added twice, possibly twice, cache misses occurring there are added twice, and so on. Cache misses occurring here are added only once, but it's fine because it's a lower bound which we want to construct, so it's good. Now here, this is a very usable sum, it's a very usable bound, but it's not enough by itself to have a bound for the optimum, we will also compute a value using these TIs for the expected cost of the marking algorithm, of the randomized marking algorithm. So for our next trick, we will just now we give an upper bound for the expected cost of the algorithm, of the randomized marking algorithm, of course. Now, how we will do this? We will do computation for each phase. So for each phase, we compute the expected cost in that phase. Of course, in that case, we only have to sum these things. We compute the expected cost. Now again, I'm just zooming in. Okay, so for the first phase, I will just spend k, but that's the optimum. In all the other phases, there is the beginning of the phase, and there are ti new elements, and of course k minus ti, well, cached elements, I would say, because in the beginning they are cached. And in the beginning, the cache content is just k unmarked, because when we begin the phase, we just drop all the marks. So we will have k unmarked entries in the cache in the beginning. Now, of course, the order might ruin some probabilities, because, for example, if I have, say, 1, 2, 3 in the cache, and then it's a possibility that I get, say, the 3 first. No, it's not a possibility, because the first element is always a new element. So I get the 4 first, and then I get the 3, and then I get the 5, say. Or another option is just I get the 4, get the 5, and then I get the 3. So that's 2 different inputs. And if you just consider the costs, then with 1/3, 1/3, and 1/3, we just discard either the 1, and in which case we will have the 2, the 3, and the 4 marked, or we discard the 2 and we will have the 1, 3, and 4 marked, or we discard the 3 and we will have the 1, the 2, and the 4 marked. And in this case we will have, so it's fine, so it's 2, 3 marked, and 4 marked. Here comes the 3, that's also fine. I will have the 2, the 3 marked, and the 4 marked. But there I will have 2 possibilities, of course, and I will just either get rid of, so it's 1/2 and 1/2. I get rid of the 1 and I will have 2, 3 star, and 4 star. and here I have the 1, the 3 star, and the 4 star if I get rid of the 2. Now for the other possibility, if I get the elements in this order, then again I will have these 1/3, 1/3, 1/3 probabilities, and then I will have 2, 3, 4 marked, and then I will have 1, 3, 4 marked, and then I will have 1, 2, 4 marked, and then if I get the 5, I will definitely pay for the 5, so it's 1/2 and 1/2. It's definitely paying for the 5, so it will get 2 4 star, 5 star, and then it's 3 4 star and 5 star. Here it's again 1/2, 1/2 if I'm just loading the 5, so it's 1 4 star, 5 star, and then it's 3 4 star, 5 star. Or I can just do this all day, so 2 4 star, 5 star, or 1 4 star, 5 star. But the difference is there is a chance that this 5 kills the 3, kicks out the 3 from the cache, and then we have to pay to include the 3. So now it's free, but here the 3 is an old request, a cached request. It was originally cached, but you have to pay for this, and this is fine. This in this case is new, and this in this case it's also kicked out. Now, if you just compute the probabilities, I mean the expected costs for these two inputs, then you get that from this point on, because till this point the cost is the same, so when we already processed the 4, at this point the algorithm won't pay for 3 here and there. Here for 3 we are paying with probability 1/2 and 1/2, so it's 1/3. So this guy here is a paying, this guy here is a paying transition. Okay. And then we will definitely pay for the last entry, which is the 5. So it's a probability of 1/3 times 1 for the last request. This guy here is 1/3 for 2. This guy there is 1/6 times 2, because we have to pay for the 3 and we have to pay for the 5. And this guy here is 1/6 times 2. Now the sum there is just 2/3 plus 1 plus 2/3, which is 4/3. Now let's analyze the other input. So for the other input, we will have from this point on, when we get the 5, then we definitely pay 1, 1, 1, 1, 1, and 1. And then when we just get the 3, we have to pay in this case, which is 1/6. We have to pay in this case, which is 1/6. We have to pay for this, and we have to pay for this. So in this case, I will have 4 times 1 over 6 times 2 coast plus 2 times the 1 over 6 times the 1 coast. What I want to mean is that if you just compute this, this is 4 over 3, this guy there, right? So it's 8 over 6, which is 4 over 3, plus, and there is a plus. This is not the end result as before, plus 1 over 3, which is 5 over 3. So this means that for this input, 1, 2, 3, 4, 5, 3, the expected cost of the algorithm, of the randomized marking algorithm, is larger than for this input. And as you see, it's in general larger, so the worst possible input is that for the randomized marking, if the phase begins with the new elements, so it starts with the Ti new elements, is the worst. So, since we have to compute the worst possible scenario's cost, because we want to create an upper bound for cost, we will just deal with these sort of inputs. So it's enough to calculate the cost of a phase if the new elements arrive first and then the old elements arrive. So, because that's the worst scenario. So we compute, so we upper bound the expected cost of the algorithm for the case, for the worst case. Which is when the new elements arrive first. Now, what's this? When the new elements arrive first. So here, what we have is the new elements always induce cache misses because they are not in the cache, because in a marking algorithm, after the end of the phase, you will have exactly the elements requested in that phase. So for the new elements, you will always pay. So new elements, the new requests in a phase always induce cache misses. In a marking algorithm, even if it's randomized, always induce cache misses. So in the ith phase, that's the cost of Ti. Now, so it's enough to compute that the expected cache misses, expected number of cache misses, by the cached elements, so all the elements if you prefer, now this can be computed as a sum, as a probabilistic sum of other probability variables, how you call it, random variables. So it's just the sum for each new request, or for each cached requests, the probability of the given request induces a cache miss. Because the total number of cache misses is just the sum of the cache misses induced by the elements, and since the expected value is additive, it doesn't matter whether they are independent variables or not. It means that for each cached element we just have to compute the probability. So what's this? Now, what is the probability of a cached element inducing a cache miss? So it's just like this. So first I have a cache. Okay. Then nobody is marked. And then a number Ti of new elements just arrive and they start to bombard the cache. And then there will be some cached elements, C1, C2, blah blah blah. In total it will be Ck minus Ti, because that's the number of these guys. So I will compute the probability of C1 inducing a cache miss, then the probability of C2 inducing a cache miss. That will be the expected value of the cost induced by the second cached elements, and so on, and the probability of this one, this last guy. So that will be say Pj, the probability okay, so probability of the jth cached entry inducing cache miss. I will just go back for our example what I'm talking about. So for example here 4, 5 and 3, this guy 3 was the cached element, but there was a probability of 3 inducing a cache miss. It didn't induce a cache miss on this path and on this path, but it induced the cache miss on all the other parts. So for example here the P1 will be say just 2/3, because 2/3 is the probability for the first cached entry to induce, in this phase, to induce a cache miss. So for example I would get 2/3 for this guy. So I will try to compute this for each possible index. Yeah. So how should I compute this? So it depends on many factors. For example, it will depend the number of new elements. So if I'm just trying to compute the Pj, then I have a number of elements, okay? And these are the new elements, Ti. And then I will have a number of cached elements, okay? Their order is not terribly important. And then I will have this jth element, right? And the important thing is here the number of unmarked elements. So I will have a recursive formula of pj, a recursive formula of the jth free element inducing a cache miss. It will depend on the number of unmarked elements in the cache, still in the cache. It will depend on the number of new elements arriving in the cache, and it will depend on the number of originally cached elements in the cache. But it doesn't really matter at that point whether they are originally cached or not. It matters that they are cached at that given time point, so it will have some number of cached elements. It will be the number of not cached elements, and there will be a number of unmarked elements in the cache. So for example, and P will denote the probability for that one. So for example, if I'm still free, the starting point is that CG is cached at this point. So if CG is cached, and I will introduce some variables for these quantities. So U will denote the number of unmarked elements, N will denote the number of not cached elements, and C will denote the number of cached elements before CJ. So P, U, okay, if there are absolutely no new elements, then of course all the cached elements will just get their slot and they won't discard me, so I will still there if I was a cached element. So it doesn't matter how many cached elements are, the probability of me inducing a cache miss is precisely 0. So if there are no new elements, then there is no choice, there is no possibility of me being thrown out from the cache, because everyone just finds its place. Now otherwise, if there are more elements in the cache, so if I have some number of new elements, then what happens? If n is larger than 0, so if n is at least 1. Now here, this first element which arrives just picks an unmarked element randomly. I am one of the unmarked elements, since I'm cached, and I will arrive in this phase, but I haven't. So here there is a possibility that this guy, the first guy, will just destroy my place. This has a probability of 1 over u. So this is the possibility that this guy immediately destroys my place. Okay, that's an option. Plus, there is a possibility that this guy will just move to some trash location. Trash meaning that amongst these guys it doesn't hit any of their cells. So since there are u unmarked elements in the cache, and there are c cached guys, and there's also me, CJ, this is the number of slots, unmarked slots in the cache, which are not a problem if the new element destroys it, so it's over u, okay, times the probability of having one less unmarked element because I marked it, and one less new element, and the same number of cached elements. And there is also another term, because it's also a possibility that this guy here arriving first will just kick someone out who was originally cached element. Now what happens is that the originally cached element at that point becomes to be a new element. Becomes a new element because there it won't be cached anymore. Now this happens by a probability of C over U times, and in that case I will have one less cache slot than I had previously, but the number of new elements remains the same because I lost one box and a new box emerged. So it will be not cached at that point, and the number of cached elements will be one less. So that is the probability which I am trying to compute, and it has 3 variables. So I'm just zooming out a bit just to see how many space I have, and not so much, I guess. Yeah, here I have. So I just try to copy these two things. So U0C was the base case and it was 0. And for other cases, P, U, N, and C are just 1 over U plus U minus C minus 1 over U times P U minus 1 N minus 1 C plus the last term was C over U P U minus 1 N and C minus 1. Okay, so for this recursive formula I have to compute some bound. So I say that in general I have some conjecture that this should be so in general P, U, and C is just smaller than or equal to something which is, say, N divided by something, and the something is, say, the number of unmarked elements in the cache, maybe, minus, say, the elements still arriving before me, maybe. So if you have these sort of recursive formulas, then you can just guess something and you just verify whether it works out through the induction. So for this particular case, this is good because here n is 0, so on the right hand side we have 0 over u minus c, which is 0, so of course the probability is 0 in that case. Now for this part I will just try to get the bounds. So for this guy, if this holds for small values, so for small values of u, say, it's an induction on u, so I can use the induction hypothesis, which means that it's smaller than or equal to 1 over u plus u minus c minus 1 over u times n is n minus 1 there, divided by u minus 1 minus c, yeah, plus c over u times, okay, so here I have n divided by u minus 1 minus c minus 1. Okay, Now that seems to be a complicated expression, so let's try to simplify it. So for example, here u minus c minus 1 is the same as u minus 1 minus c. And that is great. So and then we just have here, n divided by u minus 1 minus c minus 1, so that's just u minus c. Okay, so and here we have 1 over u, that's great, plus n minus 1 over u plus something which is completely different, so it's c times n divided by u times u minus c, right? Now this is just n over u. And this is just n over u times c over u minus c. U minus c. Which means that this war sum is just n over u times 1 plus c over u minus c. Okay, and this part here is just, so n over u is the same, times u minus c plus c over u minus c. Right, I just moved this one over and put it into the denominator, and then we can just cancel out these guys, because minus c plus c, and then I will have u divided by u minus c, and then I can cancel out u, and then it turns out to be n divided by u minus c, exactly what we just hoped to prove, which means that this is a good formula for this recursion, and it means that the first cached element will induce, so the first cached element will induce, so originally there are k unmarked elements, there are ti new elements, and there are 0 cached elements appearing before the first one, before the first cached one. So in that case, the n divided by u minus c is n, which is ti, divided by k minus 0. Now the second cached element will have c equal 1, because there will be one cached element appearing before the second one, of course, so it will induce ti divided by k minus 1 cost. The third one will induce ti divided by k minus 2, and so on. But since there are at most k cached elements and k minus 1 cached elements, since the first element of the phase is definitely a new element, it's always a new element, this means that in total the sum of the probability of the cached elements is at most ti divided by k plus ti divided by k minus 1 plus and blah 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 plus ti divided by 2, because there are at most k minus 1 and we have to decrease this value there, because the second one, for the second one we had minus 1, for the third one we had minus 2, for the k minus 1 we have k minus 2, which is just 2. Okay, so this is the sum, and this is an upper bound for the expected cost of the cached elements occurring inducing cache misses. And if we just add the cost for ti for the new elements, that's the total cost in the ith phase, which means that the total expected cost, so the expected cost of the algorithm, I will check whether I have any more place left in my small algorithm nose, so I'm just moving here then. Okay, so which means that the expected cost in phase I is at most, say it was ti over k plus ti over k minus 1 plus blah 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 plus ti over 2 for the cached elements, plus ti, well, divided by 1 if you wish, for the new elements, which is just the sum of the ti's, which is just the sum of the 1 over indexes multiplied by ti, which is just ti times the sum of, say, j moving from 1 to k, 1 over j, right? So it's just 1 over k plus 1 over k minus 1, blah blah, plus 1 over 1. Now, what's this? This is called the harmonic sum. Google it if you wish. And the harmonic sum is known to be at most 1 plus the logarithmus natural, so it's the logarithm of k times ti, of course. So this bound is a known thing for the harmonic sum, that the sum of the reciprocals is approaching 1 plus logarithm natural of k. It's basically around this guy. So what we have is that the expected cost is at most 1 and that the optimal cost, so the total stuff is just the sum of this. So the total cost, total expected cost, is just we sum the expected cost for each phase. Total expected cost is just the sum of the ti's times 1 plus 7k, because k is independent. K is a fixed value, is the size of the cache. So if in the first phase I pay this guy times t1, in the second pay I pay this guy times t2, and so on. So for total expected value, so for the expected value total, I pay this amount, and the optimum, at most, the optimum was at least 1/2 times the sum of the TIs, which means that the algorithm divided by optimum, the expected cost of the algorithm divided by the optimum, is at most, and these sum TIs magically cancel out each other, and what we will have is just 1 plus lnk divided by 1/2, which is just 2 times 1 plus lnk. So this means that the randomized marking algorithm is 2 times 1 plus lnk competitive. So the randomized marking algorithm is this competitive, which is much better than the general K competitiveness which we know for the marking algorithms in general. So this means that by using randomization we can improve the competitive ratio very much. So in general, this is just lnk competitive, which can make a huge difference if, say, I have a cache capable of storing, say, 1 million entries, because in that case, if k is 1 million, it's a huge difference to pay 1 million times more than the optimum, or just the logarithm of that twice, because the logarithm is of 1 million is something like around 20, I would say, and the logarithmic net rate is even less. And for 20 twice 10 it's just 40 times more. So on average, in expectance, this randomized variant of the marking algorithm will just spend, say, 40 more times than the optimum would be if you have a cache of size 1 million, and the deterministic one, the deterministic marking algorithm, for some input would pay 1 million times more than the optimum. So it's a very good thing to have randomization added to the mix, because it improves very much the competitive ratio. But as you see, it's not that easy to analyze in all cases. So but if we can analyze, usually it turns out that it's much better than the best deterministic algorithm. So that's all for this video. Next time we will have some introduction to game theory and its connection for proving competitive ratios. Till then, bye bye.